welcome. Thanks for coming to my talk. My name is Sebastian, obviously. And today I want to talk about a subject that I think is very important, but we don't hear many talks about it. And that is debugging, obviously. Debugging in general and also debugging C++ code in specific. Because, well, I don't know about you, but I have to admit I spend much more time debugging stuff than I sometimes spend writing and programming stuff. And because this is the last talk of the day, I have some interactive elements, some little quizzes, because I brought my best bugs. The ones that I could fit on a single slide, essentially. So before we can think about what it means to, well, debug, we first have to think what it means that our program actually has a bug. So maybe we can say that our programs have some kind of specification of what they're supposed to do. And usually that is more or less implicit. Maybe it's partially written down, but it's mostly shared maybe between you and your teammates. You have some common idea of what your program is supposed to do. And maybe you have some specific regulatory requirements, and then probably you write more stuff down. And now we mean that our program has a bug, of course, colloquially, when the behavior of our program does not conform to that specification. But unfortunately, our customers are not so nice to tell us where the bug is, but they send us bug reports. So at best, these bug reports are symptoms, descriptions of symptoms, and now we have to figure out what the actual problem is. So the first problem that we have to solve when we want to write, like in the bigger picture, or when you ship software that's relatively free of bugs, is we have to find out what bugs we have. So we want to get as many bug reports as we can. So this is one bug report. You can see from the date that I remembered this bug report when I wrote this talk, because it is not a very good bug report, obviously. It is a bit short in details. But I do remember that I could figure out what the problem was. You see, despite the language, it was a British person, I think. So we want to get better bug reports that are more helpful. So what ways do we have to get notified that our program is doing something wrong? Maybe it will crash. Maybe it will dump core. Maybe it will display an error message, write a line to a log file, or just generally show some describable and observable misbehavior. So how many of those do you notice? And more specifically, how many of those will you notice when they happen on a client's machine and not on your own machine? And now, what the first step will be is that we want to get as many information from our customers as possible. We want to know when our software is doing something wrong. So luckily, we are programming in C++, so the first thing that tells us we have done something wrong is our compiler. So we have type checks. They tell us, they prevent some kinds of bugs. We can help the compiler out a little bit by writing static asserts whenever that is helpful. We can compile, or we can calculate stuff at compile time in const and const-expr statements that prevents an entire class of bugs because compile time evaluated statements can't have undefined behavior. And there was a very nice talk about that at CPPCon once. Now, after compilation, you hopefully have some unit tests. They catch some more bugs. Your test department hopefully has some automated testing that catches even more bugs. But even if that all works well, you will probably ship software to the client that still contains bugs. So what do we do at runtime? What can we do? And we, for example, at ThinkCell, we have a very strict policy. So whenever we do a call to an external API, we check we always check the return values. And we check the return values and distinguish what are, let's say, expected return values and what are unexpected return values. And then we handle the expected ones, and we just report the unexpected ones to our error handling backend. So, for example, when you try to open a file, it is probably always expected that the file is not there, that you do not have access rights to that file, or maybe some temporary permissions error prevents you from opening that file. So it's locked on Windows, for example. So these are probably expected, can always happen. But it would be very unexpected if suddenly create file would return error out of paper. And if it did, then I would certainly want to know and would want to figure out what's going on. So we check all the return values. We also use asserts a lot to assert preconditions, postconditions, and we keep those in release builds, in optimized builds. So they ship to the customer, and they will also tell us if something went wrong. So they would tell us, hey, this precondition failed. Maybe the assert is wrong, but maybe something else is going on. So what we are trying to do is to keep our software on that track of correct behavior, of the intended behavior. And whenever it goes off that path, then we want to know. There was an entire talk by my boss, Arno, at CPP Now about this approach to error handling in a bit more detail. And what this ends up as is this thing. So that's our database interface to all those bug reports that come in. And you see we can filter them by operating system where they occur. We can filter them by build they happened in. We can see the line in the source line where that happened. We can even see some frequencies. In what build did that occur? Is that maybe a long time ago? And we can quickly filter which ones are the most frequent ones. So we should look into them first. Which ones are specific to some environment, some operating system, for example. So that's extremely helpful in catching bugs that happen maybe only in specific environments. Maybe these are issues we could never reproduce in-house. They only occur at specific customers in specific environments. So that's a very good step, the first step. Get as many bug reports as you can and write your software that way. Now, you did that, and now one of those error messages pops up. One assert fails on a tester's machine, on a client machine. What do? Do you do anything? Do you let him report this through some error reporting, bug tracking mechanism? Or do you have a process in place where you can just come over to you and ask you, hey, there's a problem on my machine. I think you wrote this. Can you look at this? You know nothing else. You don't know if that's reproducible. Is that a frequent issue? On what machines would that happen? Is it worth having a process in place where you can look at such a single occurrence of a problem? And I would say it's very much a good idea if you can organize development that way so that you can still do that. Because there's this famous quote by Gordon Ledwin, the architect for MS-DOS4, who said 1 in a million is always next Tuesday. And what he meant by that was that computers had become so fast that even a bug that had only a 1 in a million chance of occurring would probably occur by next Tuesday. So if your tester comes over and says, hey, I have this problem, you want to look at it, maybe that's your lucky day. Maybe that's the day where you find some issue that is super hard to reproduce. You will never see it again. But if you ship this software, 1,000 people will have this problem. But what can you do in such a situation? You don't know anything else. And at the very least, you can look at it, and maybe you can form some hypothesis on what went wrong, what the cause of the symptom is, what the assert was you didn't write that would have caught this problem earlier and that might have been more helpful. So that's the least you can probably do. But in some cases, you can actually fix the problem by looking at it. So that's the first little quiz we have. So I have a very simple system. I have several processes that share some temporary file. And that temporary file has also a pretty simple structure. So data can only be appended to the end in a single block. And different processes can read those individual segments of the temporary file. And a process can say, I don't need that segment anymore. And then we will just mark it as being deleted for now. And later, when somebody else comes along and says, hey, I also want to append data to the end, we might compact all those empty segments. So now, I had written this, and somebody came over and said, hey, I have I have this message here that says, well, somebody tried to read from one of those segments and the data format was wrong. So clearly the data had been corrupted. Now this has 3 operations, this shared temp file. I can append a block of data to the end. So then I take an exclusive log on the file. Maybe I compact those deleted segments, and then I append the data to the end and return some handle because I need one level of indirection. And we can read from such a handle, then we only take a shared log on the file, and we copy the data out. And last but not least, we can delete one of those segments, which just means we set a flag for now. So something here is wrong. Who has an idea what might be wrong? Yes? Is it the shared log in the delete? Not quite, because we are actually really just setting the flag. It's a good idea. Typically, deletion does not need a shared log. But of course, you're going in the right direction because there's not much on those slides. So something here must be the problem. But what is it? Any other guess? Otherwise, I'll solve. So I said I'm taking a log on that file, an actual file log. And does anybody here know, is a file log a good synchronization mechanism? Sorry?
It's only, it's not mandatory, it's on Linux.
It is not what?
Mandatory, it's advisory only on Linux.
That is true. It is not, so other processes don't have to respect the file log. That is true, but I do. So that is also not the problem. The problem is something else. I had casually said that different processes access that shared temp file. And when you want to synchronize different processes, then a lock on a file is a good synchronization mechanism because it blocks the other process from accessing that file, but it does not block a different thread from the same process of accessing the file. So that's actually the problem. Because of course, somewhere everybody has multi-threaded programs, and so do we. So that was the real problem. And it was hard to reproduce, as you can imagine. But if you question your assumptions and think, what did I try to achieve here? It dawned on me that this wasn't correct. Okay, but typically debugging doesn't work that way. Typically we don't solve debugging problems by just looking at them and thinking for a long time. Typically it takes a few more steps. So debugging becomes that iterative process where you get a bug report. You think about it for some time. Maybe you form some hypothesis on what the problem could be. You test that. You're wrong. You do that again until you find out what the real problem is and you can proceed to fixing it. And now, in order to do that analysis repeatedly, we first have to be able to reproduce that problem, ideally in-house, somewhere on your own machine, in the best circumstances. So we want to reproduce the bug. Now, if a bug is reproducible or not, it's not such a binary thing. There are different degrees here of reproducibility. So in the best case, your tester comes along with a bug report, and that bug report is always reproducible in a debug build on every machine you try it on with an interactive debugger attached, and then you're good to go. But, well, you might be less lucky, and maybe it's only sometimes reproducible only on very specific machines with very specific optimization flags, and maybe you need 10 other things installed for the bug to be reproducible. And that makes things more difficult. So the first thing we want to try is to move up here, to make things that are hard to reproduce easier to reproduce. And that's typically the first thing I try whenever a tester comes along with something. Now, what ways do we have to make things easier and better to reproduce? So if things are only sometimes reproducible, a thing we should always do is to use all the sanitizers. I think, was it Alistair in the other talk who asked who knows about the address sanitizer and the UB sanitizer? Who doesn't know about them? Good. Who uses them regularly? it's not quite all the hands, but half the hands. That is already very good. So what the address sanitizer and the other sanitizers do is to instrument your code to reliably find, for example, in case of address sanitizer, issues where you use, let's say, a variable that has been destroyed already. Typically, if you're not using raw pointers here and there, typically that might also mean a variable that has gone out of scope, but you still hold a reference to it, for example. And the address sanitizer will instrument your binary, so it will tell you, hey, here you're doing this. Whereas in practice, this will very often work because the variable is still on the stack, it hasn't been overwritten yet, so the access will still read the data you expect until something changes. You change some optimization flags, you change some variable, and suddenly it's not reproducible anymore. So the address sanitizer and the other sanitizers help with that. Now, if something is only sometimes reproducible, it might, of course, be some complicated timing issue. Maybe several parts of your application, several threads, several processes are interacting in a very specific way, and when they do that, then something goes wrong. And you can try to write stress tests. Maybe you can execute the part that goes wrong much more frequently to force the issue to appear. Maybe you cannot attach an interactive debugger to your system because that destroys the timing and the bug is not reproducible anymore. But maybe you can still write to log files, and that is fast enough and allows you to gather information in such a situation. Writing a stress test can not only mean to do something very frequently, very often, to force an issue, it can also mean to write code to test assumptions. It can mean to write code that does a few statements in a very specific order to force an issue to appear. And last but not least, maybe you can write code to diagnose the system when the problem has already occurred. So you can detect that problem and then try to figure out in code what the state of your system is. Now, if a problem is only reproducible on some machines, it's of course a good first idea to think, well, maybe it has something to do with those specific machines. So you start to collect all the data on that environment. What operating system version, what CPU is that, what version of your software, etc. And especially in desktop environments, this can mean anything. Anything can happen. It could be virus scanners, it could be DRM software, or system tools, or a misconfigured system. So there are quite a lot of things you might want to look at to reproduce that bug. And maybe it's easier to reproduce that environment in a virtual machine. Maybe you can only ever reproduce it on a client machine because you need a very specific setup. But maybe you can get access to that machine. And in the worst case, you might even get clients to ship you an identical machine, so you can work on that. But last but not least, here, it's important, as always in debugging, to keep an open mind. It could always be anything else. And it is important to keep an open mind and not discard any hypothesis too early. It could still be something else, another timing problem. Maybe those machines are just very slow or very fast or something else. And if anything else fails, then it's good to have some automatic bug reporting system like I've shown in the beginning. There are several open source versions like Google CrashPad. They allow you also to write and ship analysis code to, again, analyze your system when the problem occurs and maybe send a more helpful error message to your developer team. And if you have a really good system, you can even try out fixes on those live machines and report back if that worked. But I have to admit, we only did this once in 20 years, I think. Maybe you can only look at the program state after a problem occurred. Or maybe you can look at program output after a problem occurred and then walk your way backwards to the problem. And that's the next quiz. So we had a customer report. Well, our software doesn't start. Okay. We could look at the log file. And the log file said there was a bad alloc exception. Now we could also look at our bug database. And we saw, well, it's actually loading some setting file that fails. And we couldn't get any reproduction, of course, but we could then ask the user to send us that specific file and try it out. And we could look at it, and we found out, well, there was some weird data in it. There was some number format data structure, and instead of a single number format, string, that string was duplicated 18 times. It was always the power of 2, and that was odd. So what's the first thing you do? Well, maybe you look at the data structure. So there was a vector of a pair, and that size t is maybe an index into the string, and the format string is what kind of number you want to insert there. And now comes the crucial information. That thing lives in shared memory, and that is, again, shared between different processes. So anybody already wants to make a guess what the problem could be? Well, neither could we. We had to dig a little bit deeper. So something went wrong maybe with the size of that data structure. So apparently maybe somebody thought it was getting bigger and bigger and bigger. So what's the size of that vector? That's the size in bytes divided by the size of each vector element. And the size of each vector element also contains the size of size t. Now, any ideas? What could the problem be? Yeah. A different size of size t, exactly, because then it dawned on us that, of course, that's not the same in 32-bit and 64-bit processes. And of course, we had both sharing the same shared memory. Exactly, that was exactly the problem. Now that we have a good reproduction that we can reproduce the problem, we can start to identify what the actual bug is. So now we are actually starting the debugging process. And of course, the moment the application crashes, the location where it crashes is typically not the place where the actual bug is. That might have happened earlier, that might have happened somewhere else in the code. And we have to walk back from that symptom, from that crash, from the error message, to the problem that we actually have to fix, that we actually want to fix. So how do we do that? How do we go back and find the real problem? Now, of course, we can use the sanitizers, and they might just tell us. And using an interactive debugger is always a good idea, because I always read that people don't use interactive debuggers, but maybe not the ACCU audience. So one first step is often, when you're faced with a large system that you're only partially familiar with, is that you want to gain an understanding of the larger system. So you want to find out who's doing what and in what order. So you want to find out, what calls are being made. And that's what people typically use printf debugging for. So you would just write a printf statement somewhere and compile, and that's your debugging mechanism. Well, what's much better, obviously, is to use a real debugger and to use debugger trace points. So these are breakpoints where the execution is not interrupted, but instead you tell the debugger to print something. You can print variables, for example, as in a printf statement. And one of the biggest advantages is you don't need to recompile your code when you do that. But tracing breakpoints are also strictly more powerful than printf, because you can add them to operating system functions. You can add them even to specific binary code addresses. And GDB and LDB are even more powerful. They can attach arbitrary debugger commands to those tracing breakpoints. For example, you can make them print the stack trace whenever a certain function is called, which is super helpful to find out where that call is coming from. They can be scripted. If you are working on a specifically difficult problem and you have to add the same breakpoints but maybe in slightly offset addresses a lot of the times, then you can write debugger scripts that do that. And they even have a Python API if you need to do something extraordinarily complicated, maybe. But again, here, a warning, as always, interacting with your program may make some kinds of bugs disappear, unfortunately. Sometimes the problem we're looking for is a bit simpler. Maybe we're just looking for a problem where our application interacts with the operating system in a specific way, and that interaction fails somewhere. And then there are specific operating-specific logging tools that we can use, so we don't have to add tracing breakpoints to every file function in Windows, for example. So in Windows, there's a process monitor, for example, that can tell you which file accesses you're making, which registry accesses you're making, etc. macOS SSD trace, and Linux has a number of different tracing tools, depending on what you're looking for. And here the general debugging advice is that it's important to know the operating system that you're working on. That's a step that unfortunately for younger programmers, you cannot skip. Because otherwise, you run into the problem that I ran into. You don't know how file logs work on your operating system, and you make stupid mistakes. Shared memory, virtual memory, the file system, does it log, does it not log files typically? All these things are, well, things we have to learn about when we're working on an operating system. Sometimes you know that an older version of your software did not have a bug. So you can compare the two in different ways. For example, you can walk backwards in your source control system, and you can try to find out where that bug you're seeing now was first introduced, using git bisect, for example. And if you can figure that out, then that has a very big advantage. You can look at that change that introduced the new bug and figure out what that change tried to achieve in the first place. And with that information, maybe you can combine the two and find a fix that fixes both problems. If you skip that, you might run into the problem of introducing error cycles. You fix the new bugs, you reintroduce the old one, etc. But you can also go through both versions in parallel. The old one that works, the new one that is broken, to figure out where they differ. You can do the reverse, essentially. You can try to disable code until the bug disappears. You can disable increasingly smaller parts of your code while the bug is still there, and track down the lines in your code base that create the problem that way. So that all requires knowledge of your code base. It can be super time consuming, of course, as everything in debugging. It can also be the quickest way. It's very hard to say in advance. And last but not least, especially when you're faced with older code, with legacy code, while you're debugging and you're rethinking what you did or what somebody else thought in the past, that's a good opportunity to improve the code. Maybe you're thinking this through for the first time in years, and you figure out, hey, there's this invariant that should hold. We should have documented that, and maybe we should have asserted that in the first place. So you can introduce those asserts while you think about them during debugging. If they are very complex and hard to check, then only make it temporary while you're looking for a problem. Introduce better programming techniques while you're at it. Introduce smart pointers, array objects, etc. That may fix bugs that you haven't even found yet, just because you clean up the code on the go. And then there are the reverse debugging tools. One of them, I think, is presented outside from the people of Undo. They let you do pretty directly what we are trying to do here. They let you walk backwards from the moment you, let's say, crash to the moment you're looking for, to the moment where something goes wrong in your program. So they record a trace of the program execution and then let you replay that in reverse order. So that exists in Windows and that exists on Linux. And, well, like I said, you have to know your operating system, you have to know your debugger itself as well, of course. Using data breakpoints, using debugger scripts, writing debug visualizers for your data types that you are writing yourself. And I think it has also been a very useful debugging skill to have at least passive assembler skills. So that leads to the next quiz. So here, I have an array of integers, of indices. And I call some function, and I pass that array. And I want to have the actual items back. Items, whatever that might be. Now the problem is this function get item from indices, I don't have the source code for. It's some external library. And now that seems to have a bug because I pass it 4 indices. I only get 2 items back. That should not happen, it should be 4. Now I would like to debug that because I would like to write a good bug report. What do I do? How do I find out what the problem is? How would you proceed? Sorry? Look at the disassembly, yeah, but then you see the disassembly for the call from get item from indices. So that's not very interesting yet. That might be very long. We have to do something else first. We have to figure out which disassembly to look at. Where is the problem? So we can use a data breakpoint. Here we say, we tell LDB, please put a breakpoint, please break, when the first element of that array is being read. The first 4 bytes of that array specifically are being read. Because that should happen somewhere in the disassembly, right? Probably close to where the bug is. Maybe that data is passed around and copied, and then you have to do that a couple of times. But here we were lucky. So that's setting the breakpoint. We execute the code. We find this. So this is something, well, it's probably something that happens somewhere. So somebody is reading that array, and then he's iterating over those elements of the array and computing something. But unfortunately, we don't find this. We find this. So who here is familiar with ARM64 assembler? 1. Who is familiar with Intel assembler? Reading it, at least. Also not that many hands, but 6 times more hands. Yeah. So it's the same for me. I still am not very familiar with ARM disassembly. So I've helpfully translated this bit. So the first thing is getting that pointer to our array, to the beginning of the array, and then it's calculating or getting that loop variable from somewhere. And then that code is accessing P with the loop variable multiplied by 8. Now why 8? We put integers in, and the integers are only 4 bytes and not 8 bytes. So that's clearly a bug. Somebody made a mistake. It should be times 4 and not times 8. And now I know that that source code has been ported from Windows to macOS. Now, anybody has an idea what the code, what the bug is in the source code? Sorry? Long, exactly. So on Windows, long and integers have the same size, and for some reason the Windows APIs like long a lot. So probably somewhere somebody mistook those 2 types and compiled it on macOS, and now it was wrong. So that was indeed the bug, and it was a very good bug report. It was quickly fixed. Right. Okay, now we've essentially done the entire process from getting bug reports, getting as many bug reports as we can, to finding the actual problem, hopefully, in our source code. And we used a lot of tools, debuggers, sanitizers, reverse debuggers. We learned about our operating system to get better at this. And these are all very important techniques. But the most important technique without which debugging becomes a very hard undertaking is that you have to be able to question your own assumptions. Because you know there's a bug. You've seen that. So something you thought was correct or something you didn't think about at all was clearly wrong. So now you have to find out what part it was. And if you always think you thought correctly, then, well, it's going to be pretty hard to find that bug. So that's the most important debugging technique, I think. Now we want to fix that problem to finish this up, right? And if we want to fix that bug, we first have to think about what kind of bug we made here. And I think there are 2 different kinds of bugs that we typically make. There's what I would call the small kind of bug. So we didn't quite write what we meant to write. we forgot something, we misspelled something, we used the wrong variable, we didn't initialize data probably, or maybe we didn't use a smart pointer where we should have. But fundamentally, we did the right thing, just in a slightly wrong way. So the fix is probably a small fix, a local change. Maybe it's a local change, but maybe we should always look at the entire code base if that local change could be made elsewhere. But like, mentally, we made a small bug, I would say. And then there's the other kind of bug. You did write what you actually meant to write, but you meant the wrong thing. You made a big mistake somewhere. Your mental model was wrong, you didn't understand the problem correctly, you didn't understand the types of input you would get correctly, or the types of output you should produce. So you need some new mental model, and you need to rethink your entire approach. Maybe you didn't understand somebody else's requirements correctly, you used the wrong algorithm, or you didn't implement it correctly, maybe. Now, how do we distinguish those two problems, those two kinds of bugs? And that is not so easy. We can't just look at it and say, aha, small fix, big fix. So let's say we have this little piece of code. We're just doing a for each over vector with pointers and dereference that pointer. Now we get a bug report that says, this can be null, this crashes. Now what do we do? Do we do this? Is that a good idea? That's hard to say. That, like in a code review, if we do a mock code review, what are the questions you could ask? You could ask, where's that vector coming from? Who's producing that vector? Why is anything in there null? If anything in there is null, is that the right data structure? Shouldn't it maybe be an unordered set or something? So there are quite a lot of questions you should ask until you can decide, yeah, it is a vector. Yes, one of those elements can be null. Yes, we're for eaching over them here. And yes, you should check if one of them is null. So there are a lot of questions you should ask until you can decide if that was a small problem that can be fixed that way, or if that's a big problem, wrong data structure, wrong algorithm, and you have to rethink your entire approach. Possibly wrong. So like I said, we have to look at the bigger picture and have to ask ourselves, what are we trying to achieve here, and do we try to achieve it with the best means we have available, or should we be doing something else entirely? Okay, now we are closer to getting done. Now maybe we have decided, we need to make a big change, we need to make only a small change. Now what should we do? So in other talks, common advice is that once you've identified what the problem is and you've understood it well enough, you should try to find the smallest fix that actually fixes the problem. Because it has the advantage that by being small, it does not introduce new problems, or it has less likelihood of introducing new problems. And while that is not wrong, I don't think it's a very good first advice. Because maybe people tend to listen to the small part and not to the smallest fix that really fixes the problem part. So we may try to jump to small fixes that don't really fix the root of the problem, or only hide one specific instance of the problem and making the other ones harder to reproduce. And over time, by accumulating small fix on small fix on small fix, your code quality will degenerate. Your code will become harder to understand, and the number of bugs you will make will just increase. I would rephrase this. I would start the other way around. In an ideal world, without any constraints, what would the ideal solution look like? Supposedly, after debugging some issue, you've learned quite a lot about it. So how would you write it if you would start fresh? And at least you should try to move towards that solution. And now you come back to the real world for a short moment and you think, well, I do have a couple of constraints in the real world. money, time, but maybe I also, well, just want to ship a fix quickly to existing users. But now you can decide, well, what's the quick fix I'm doing for like a small update? Or maybe, again, if you're working in some special environment, maybe you have to document your fix especially, or get it valid, get it, what do you call it? Get it vetted by somebody else. So you can make the small fix, but then think about the big one, what you should really fix, and then try to at least move in that direction. So that's how I would phrase it. And then when you've actually removed the bug, come the next steps that we also like to forget sometimes because we have other things to do. So why did that problem happen in the first place? Was it hard to program correctly and easy to program incorrectly? A common problem when you're programming C++. Was there missing something in your code base? Some feature, some algorithm, some helper that would have made it easier to do the right thing instead of reinventing the wheel and then doing it slightly wrong? And can we prevent that problem from happening again? Can we make the same fix we just made somewhere else? Can we introduce that missing abstraction that would have prevented our problem? And missing abstractions can mean so many different things. So here again, actual real problem. So we had this, some variation of this in our code base, a surprising number of times where we have some vector, you sort it, and then you want to have the unique elements in that. We had this, I think by the time we found the problem, we had this 74 times, the same pattern. Does anybody have an idea of what could go wrong here? If you do this over and over again, what will you get wrong eventually? Because there's some subtlety here that you have to do correctly. Well, the sort and the unique, they have to use compatible predicates, but they use different ones. One uses a less and the other one uses an equal. But when you program them manually and you just don't use ranges less and ranges equal, then it's easy to get this wrong. And of course, in practice, somebody did get it wrong. So here the missing abstraction was, well, write one algorithm for your code base. If you do this 74 times, then it's probably worth some function in your code base that only takes one predicate and generates the other one correctly out of, for example, the less predicate. But it can mean different things as well. Error handling is super difficult. Error handling is something I said initially we always do. And it's a pain. Here is how it looks when you try to open a file on any POSIX system. So what's the success case? Any non-negative returned value. That is different for other POSIX functions. There are cases where you want to retry when it returns interrupt. There are cases I don't care about that may happen, like the file doesn't exist, I don't have access to the files. These will happen, I return nothing, I'm happy. And then there are other error codes where I don't know how that should happen and I would like to investigate because maybe I can do something about it, etc. So that's error handling. Same on Windows, where the pattern is maybe slightly different. You have Windows API functions like getClientRect, and on error they return 0. And when they return 0, then you have to call getLastError and report that. You can make that easier because it happens so often that it should be easy. Nobody should write getLastError anywhere. Okay, and now we are almost done. And all we have to do is wrap things up. And we have to, of course, document what we did. And we have to document stuff, ideally in the code, where it doesn't rot. We sometimes have to write why we did something, but more specifically, I think comments should answer the question, do we still need this? Because your future self will come along and wonder, not only why did we do this, but when can I remove this? So it's good maybe if you have references to your bug tracker that says, hey, this was a workaround for some bug in Windows 7, and we don't support that anymore. So you can remove that ugly hack. And of course, we do code reviews to figure out, well, to let us explain to each other what we try to do, to figure out if there was some problem in our thinking. Everybody hopefully uses version control by now, and tests, maybe even tests on random input, so we don't write tests exactly for the cases that we do support, but tests for the cases that might be difficult. And with that, we are really, really done. And we have found the bug, and we have fixed it, and we've documented it, and hopefully we made our program a little bit better. And here my talk is done. I hope it was useful, and I'm open to questions. And I have one more quiz, because we definitely have the time for that. If you want to, we have one more C++ related bug, if you want to. Okay. So we're trying to read data via HTTP. We have some asynchronous HTTP API. But we don't actually need all that fancy stuff, but we need to satisfy that API. So we need to write some delegate that has a callback, and that callback will be called by our asynchronous HTTP API. And when we get new data, then we lock a mutex, we check, did that download succeed, that part of the download. Then we store in our state, hey, I have new data available, or otherwise we store in our state that some HTTP error occurred. And when we're done with that, we release the mutex and we notify a condition variable. And now on the other end, we have somebody who tries to do a synchronous HTTP request, because we don't actually need all that fancy async stuff. So it sets up the HTTP API, and then it waits for the delegate, essentially. So we wait for the lock. We wait until the delegate tells us, hey, I have something. Either I have data or I have an error, and no one can stop. And if it has an error, then we throw an exception, because, well, it just failed. We don't care what happens. So this is, no, you shouldn't do that on slideware, but this is subtly wrong. And it will fail. We had something like this in our back end, and it failed 1 in a million, like the quote. Failed 1 in a million. Rarely, but it did fail. So, and it does violate at least one CPP guideline. Hopefully, so luckily there's a guideline advising against this. What is wrong? Sorry? I have a microphone. Now the mutex is locked. The mutex is locked. That is correct. Somebody else was raising his hand. Yeah. What do you mean here? Can you speak up a little bit? What is the bug? Yeah. No, that one. Okay. I see. That's a simplified example. No, that thing is only ever called for one other thread, not from the main thread, but one other thread. Yeah. What else?
I just don't understand the code. What is resetting any state waiting?
It's just waiting, nothing. It's waiting initially. And we yeah, we probably should. Yeah, like we probably should somewhere when we do something with the data. That is correct. So, of course, it's something with the mutex and the condition variable. When does this wake up? What's the problem with that wait? Or one?
You can have a spurious wake-up. Exactly. What happens if I have a spurious wake-up?
I would run the function and it would not be true, I guess.
Yeah, it would not be true? Well, unless I'm exactly there in the left-hand side, then it will be true, right? When I'm here, when that execution, when that thread is exactly at that closing break. The mutex is released, ME state has flipped, and it says error, for example. I get a spurious wake-up. I wake up, I have an error, I throw an exception, I delete the delegate, boom, my notify all goes to a destroyed member variable. And that is why, is that clear? Did everybody follow, or does somebody have a question about that? That's why the CPP guidelines explicitly say that you should always write the notify inside the mutex. It seems like this would be somehow inefficient because then this guy wakes up, but you still have the mutex over there, so it has to wait one more. But apparently, I didn't verify, but apparently every implementation optimizes this away. But if you write it outside the mutex, you have to make sure that you deal with spurious wake-ups correctly. All right, so that's the last bug I have brought. Now, very happy to answer your questions. And I have a microphone, if you want a microphone. Yeah. Do we have to switch this on? No.
My question was that in, I think, most of the examples you've shown, problems were tied to kind of C-star programming. You go through a void pointer interface, you kind of bypass the type system. Some of them also due to be compiling things in different modes, and maybe you're linking them, well, I guess not link, you're going through shared memory, which is sort of outside the realm of
the standard.
C++, yeah.
That is true. Or some of these examples aren't. The binary code example, well, this is not so outside of the standard. I think you're referring to.
My thing is, why couldn't you just enforce a good, using typing everywhere to solve some of these issues?
Oh, we do that. We do that. But some of these, I mean, here the types won't save you because, well, it's compiled code. So I don't know that they made a type mistake. Why didn't they compile this?
Yeah, but you should compile. Every code should be, if it's compiled with different settings, that's an ODR violation and undefined behavior anyway.
Yeah, true. That is true. But I mean, that's the real world. Sometimes you call other people's binary code. Very often, you typically do that on your machine as well. Shared memory is special, but there the lesson is actually use static asserts. That what we did in the end was write a static assert that asserted on each build that the size of that data structure is the same, so that we don't get any surprises. That's what static asserts do for you. So when we're compiling 64-bit and 32-bit, the size of that shared data structure must be identical. So I would say that as long as only our code is concerned, the type system does that for us. But when you're interfacing with other processes or with external libraries, then that doesn't work so well. Right.
All right, makes sense. Thank you.
Any other question? Is that a question? No, yes, you were. Yeah.
Maybe, I wanted to ask, did you actually have a client ship you one of their machines?
Sure.
Really?
Sure, laptops, yeah. Imaged, they have the specific way of imaging their machines, and then only then.
And then how do you debug on that?
Remote, Visual Studio Remote debugging, for example. So you don't need to install anything, it just opens some ports, and then you can debug it. Yeah. Oh, yeah. I mean, already for
1,000 different licensing reasons, it's very often super hard to reproduce an environment. You know, if they have some specific tools they install, and I'm not sure how common that still is, that people actually write desktop software, but I think in my experience that environment is super hostile. I mean, everybody is doing crazy things, especially on Windows, hooking system functions, hooking windows, and these things interact in the weirdest way, and sometimes it's just Windows itself that where you can have so many extensions in so many different places. You can have Windows Explorer extensions that add an item in the Explorer menu, you know, right-click, print as PDF or something, and that actually can affect you in a PowerPoint process, because Windows will instantiate that thing somewhere. So
yeah, I think you had a quote earlier that desktops are the worst environment.
Yeah, that was on one of my first slides. Yeah.
I think Python is the worst environment.
Python is
maybe
the worst
that's a different talk.
Python is the worst environment. Any other questions? Yeah.
Actually, on your last bug, apologize.
On the C++ one.
Yeah, for the last bug, I wonder if things like thread sanitizer or even valgrind with lgrind would have helped.
If the thread sanitizer would catch that.
Yeah.
Good idea. I didn't check.
Okay. Fair enough.
I don't know. Yeah. Okay. Any specific stories? We can do this kind of like a sharing thing, sharing like specific painful debugging stories. Okay, otherwise I thank you for your attention and for coming to my talk. And well, you can find me outside at our booth if you have any further things to discuss. Thank you very much.